our COBT listeners and viewers, it's Maynard, Mike, and Robbie here with something we're super excited to do. For a long time now, we, like others, have been talking about the produced water issues and opportunities in West Texas and New Mexico, the Permian at large. And I think we've been thinking about when is the right time and who are the right guests and how could we possibly talk about this on a COBT. And I think we've hit the mother lode here of great water conversation. We're going to talk with Adrianne Lopez. Adrianne is the Research and Development Director at Texas Pacific Water Resources. Why we've become so enamored of Adrianne is when she gets into the science and the chemistry of desalination and all the things that can happen with water, beneficial reuse, etc. She's a real expert, not just at the economics, but at the science. And so she's on the cutting edge of it. Adrianne, we're really delighted to have you join us.
Thank you so much for that introduction, Maynard. I'm absolutely delighted to be here and cannot wait to discuss more about produced water. It is one of my favorite things to talk about. As you said, I get way deep in the weeds talking about the science behind the treatment and everything. So I'm very excited to be here and have this conversation with y'all today.
Well, it's going to be super fun. And then we've got like a real breakthrough here because Scott Tinker is returning. He's joining an elite group of people who have been on COBT 5 times. Scott, I don't know if you knew that, but you're a member of the 5 Club now. Very big. But to really spice it up, we have not just Scott Tinker, we've got Derek Tinker. Derek is highly analytical like his father and runs the Agnostic Data Group, and he'll be talking a lot about water from his vantage point. Scott will be talking about it from, like he always does, from multiple angles: the opportunities, the issues, how it can help oil and gas, how it could help data centers, how it could help power, why it is, how it could help ag. There's so many angles to this. And when it comes to multiple angles, Scott, you're the best in the business. So welcome to, it looks like the Tinker brothers, but it's the father-son Tinker team. Thanks for joining us, guys.
We're glad to be here. And it is great to have my kid. Usually you give me a nice intro, Maynard, and I say, gosh, I wish my kids could have heard that. But, so I had to bring him, now you can hear it. But it's great to be here with you. And it's great to have Derek as well. He's an engineer and physicist and runs this data company and across the board, but deep in the agriculture side as well. And then I wear lots of hats. So we're looking forward to visiting with you and Adrianne and seeing if we can make some headway here.
Well, I'll tell all of you, and Robbie and Mike know this, we have been looking for what is the produced water show that is useful, productive, informative, and talks about the opportunity as much as the challenge. And I'm really optimistic we found it here. Mike, what would you tell us as we jump in with the team about the markets or the world or anything else?
Yeah, I think about last week. I mean, we had the fundamental AI guys here, and my lead-in was really the mid-year review, sort of the winners and losers. And I'd say the theme of the market this week is sector rotation, market rotation is what we've heard quite a bit of, and we've only been 2 days in here, but we saw a little bit of this last week as well. As far as the bond market, 10 years around 4.52%, but the 30 years above 5% again. No real economic data this week, but next week we're going to get the CPI and PPI data. So we could have some fireworks in both the bond and equity markets next week. So that's what we're looking out for. As you said a little earlier ago, the broader markets, it's all about sector rotations. Last week, the last couple of weeks, we talked about how big tech had underperformed this year and industrials were outperforming and chip stocks were outperforming. So there was definitely sector rotation and even the small caps as well. We talked about chips and semi companies being the big winners this year. That's all basically been not all been taken away, but that's shifted quite dramatically here in the last week. You've seen the SOX index is down 10 or 12% here in the last 5 trading days, and the Mag 7 stocks are up about 5%. And so it looks like there's just, some rotation going on now that we're past mid-year. We'll see if that lasts beyond a week or two, but that's what's happening right now in equity markets. As far as the energy equities, obviously they're up a couple percent this week just because crude oil's up, a buck or two here over the last couple days. As far as what we're looking out from an energy equity standpoint is that, in 2 weeks time frame, you're going to start to get into Q2 earnings. The oil service companies are going to be leading off. Guys like Weatherford, Schlumberger, Halliburton, they're going to be reporting Q2 earnings. And so a lot of people are going to want to find out, hey, what is the early read on what E&P spending is going to be in the second half of the year? As you recall, Diamondback increased spending immediately in Q1. That was their announcement. Back then, oil prices were at $95. Now they're at $70. So it will be interesting to see what E&P say for second half. My guess is they're going to say they're going to continue what they've done in the first half of this year, which is sort of maintenance type spending. As far as the utility and power sector, what we just said with tech stocks, I mean, some of the best, utility power stocks this year have been sort of these power related companies, these large generation companies like Caterpillar. You had the INEO IPO. You've had like these, distributed generation companies, that be Liberty, SCI, we're up substantially. They've pulled back here over the last week, and it's really on the back of that trading. Have they run too far? Is AI spending going to start to pull back? And so we'll see how that goes. But definitely, that's where we've seen some weakness here in the last couple of days, in the last week or so. As far as oil, we already said it. Oil's down about, it's up about $2 a week this week to about $70. And I think what we learned this week is there's been some ships in the Gulf that have been basically hit. And so this trade, this normalization trade in the Strait of Hormuz, I think everyone thought was going to happen. Maybe we're a bit too optimistic on that, and we'll see what goes from there. I said the last thing I'd really want to talk about is natural gas. U.S. natural gas prices have moved up a little bit. They're around 325, 320, 330 in MMBTU. And that's because of hot weather in the U.S. But I mean, the real action is in the EU, in the European Union. You're seeing gas prices have moved up from roughly $14 an M to $16 an M. A lot of that was related to this LNG ship attack in the Strait of Hormuz. But what we're talking in Europe is that inventory is around 25% below normal. You're getting hot weather there as well. And this incident in the Strait of Hormuz is just showing that they're going to have to probably pay up for barrels to get that inventory up to where it needs to be by fall of this year. The last thing we really wanted to talk about on the natural gas side is the the IEA came out with a natural gas report today. They talked about global gas demand being down about 0.5% for 2026. They basically talked about a 0.5% demand decline in Asia due to coal to gas switching. And they also talked about 4% decline in the Middle East. This is the first time we've seen a Middle East decline since 1993. And so all I'd say is that, that was a pretty big wake-up call, because you know what? I think the world's been talking about, hey, we're going to be moving to natural gas. I think this growth in natural gas is going to be like this, for the next 20 or 30 years. We've seen a pullback here because of the Gulf War. And so we've had that with the COVID and also the Ukrainian war. And so all I'd say is maybe we shouldn't be thinking about gas going up every year by a couple percent. They're estimated it's going to be down. So it's something for us to watch for sure.
Awesome. Robbie, you spent a lot of time around our water discussions, convened water roundtables, been out there, done a lot of stuff. Anything you'd add on that or anything else as we jump?
Yeah, absolutely, Maynard. Yeah, I'm really excited about the topic today. There's really two major technology things I think I've dug into the most since starting here. One is AI, of course, and I've talked multiple times about that. But the other one, and maybe it's just because we're in Texas or closely connected to the oil and gas industry, but the other one, of course, is produced water. And it's a very fascinating topic because it's one of the few industries that's net water positive, right? And yet there's a big problem with it. There's so much water being generated from oil and gas production, they don't know what to do with it. So it's creating a problem. And yet there's so many industries that need water. The state of Texas need water. And so from a capitalist perspective, you're like, okay, there's a supply and demand, like this should naturally get solved, but it's not that simple. And so it's going to be fun to hear from everyone on the call today into the challenges, but also the opportunities for technology or other industries to benefit from all of this excess water that's produced.
Great. Well, let's jump in. Scott, I'm thinking you're a great place to start because, we were sharing this with you a little bit before we turned on the camera, but so many people in our audience do understand all the water that comes with oil and gas production, but not everybody understands it, and not everyone has a sense of the scope of it. and not everyone has a sense of like, the nature of the water and how easy it is to do anything with, would you mind just kicking us off with a big picture intro to the produced water, problem and opportunity as you see it?
Sure, Maynard. Happy to do it. And thanks for hosting this, Adrian. Great to be with you. Look, if we go back 15 years, as shale was really starting to come into its own across the country, Barnett, Fayetteville, Haynesville, Marcellus, shale gas, and then here comes the oil, Eagle Ford, Bakken, and now West Texas. Well, the Delaware Basin, the Permian Basin, especially Delaware Basin, you produce a lot of water with that oil. Delaware Basin, you're looking at 3 to 5 barrels of water per barrel of oil produced. So this is a huge volume of fluid. Oklahoma was having challenges with earthquakes back in those times, 10, 15 years ago, when they were disposing the water. Texas got out in front of it. I worked with Myra Crownover, actually, state rep from near the Fort Worth area, and there are earthquakes in her district. And so she said, Scott, what do we do, basically? And she hosted a couple workshops or actually hearings that summer. And from that came TexNet, something most of the industry is quite familiar with now. TexNet is a seismic monitoring network across Texas. Didn't exist back just 10, 12 years ago. And it looks at earthquakes. So when you take all that produced water, separate the oil out, you got to do something with it. And initially they were moving it, and still are, and then disposing it in deep well bores below the producing horizon. We anticipated that could start to cause earthquakes when you put that much volume of a fluid in the earth and get it near natural faults in the earth, Maynard. It's not, they don't lube them up, they change the pressure conditions. And so that pressure changes and those faults can slip. So we've seen through time with TexNet monitoring in partnership with industry and the Railroad Commission, who regulates it, the increase in both the frequency and the magnitude of earthquakes in West Texas. So then industry starts disposing water in shallow horizons. And that's okay, except we start to see some of that water coming up through old well bores to the surface. It's just a massive volume of water. Today, we're talking about somewhere on the order of 20 million barrels of water a day. 20 million barrels a day that get produced out of the basin and have to be managed. And that's old ocean waters. It is water, exactly correct, but it isn't the water you can drink. And it's not even the water you can irrigate food crops with. Something has to be done to it to make it usable. And that's the challenge. So you see the earthquakes increasing, the volume of water continues to increase with production. That's all good. But how do we manage that water in a way? Can we manage it in a way that we can create win-win-wins for different sectors around the state of Texas? And the answer is yes, but as was well said, it's tricky. It's not just an easy, oh, here's your water. Got all that water produced. What are you going to do with it? Who can take it? Clean it up. By that, I mean take the salts out and maybe some of the metals, which have a beneficial use. Cut the volume of brine in half. Dispose that. That helps. That helps with earthquakes. You're injecting half the volume. Now you have a cleanup volume. Who could take that? Well, AI needs water, big data centers. And it sounds like a lot, but relative to the amount of production, they're not huge on that scheme. You could dump it in the Pecos River. That's what's being talked about. I'm not a huge fan of that personally. I think we could do better with it. Or you could use it for agriculture. Cooling of electricity always takes a lot of water. So these data centers are saying, hey, we're a closed loop system. We're going to take some water and keep it closed, but they're only talking about the system itself, the shell and the components in it, not the power generation. That takes water cooling as well. And so they could use some of it. It has to be a certain spec. There's still going to be more water than they can use. And that's where ag comes in. And we can get into the details, but agriculture, especially non-food crops, they could take it all, plus some. And it's pretty close. I mean, we got lucky. The non-food crops are 30, 40, 50, 60 miles away from the Permian Basin. So we're not talking about huge distances here. And the farmers They use a tremendous amount of water every year, and they're producing it from the Ogallala Aquifer. And that aquifer is a fossil aquifer. It means it's not getting recharged in real time, and it's drawing down. It's getting close to the end of life. So if there's an opportunity to rest that aquifer some and use water on the surface from somewhere else for decades, that's win-win-win. Okay. So that's kind of a big picture, and happy to go into the details more on that as we go.
Oh, that's great. Maybe, Adrian, I could just ask you, because I think I'll speak for myself. As you learn about this problem, one of the things that jumps out at you pretty quickly is the nature of this water. Like if I recall, it has much more brine. It's much tougher to work with than ocean water, for instance. Would you mind your science training? Just talk about what's in this water, and what kind of, because a lot of the options and the cost stem from that.
Yeah, absolutely, Maynard. Produced water is very unique in that it has a tremendous amount of solids in comparison to traditional seawater. So we have seawater desalination techniques that are available that have existed for a very long time. However, produced water is about 3 to 4 times as salty as seawater, and it's not just salt that's coming back with this water. So this water has been sequestered underground for millions of years. It has bacteria that are very toxic. It has oil and gas in it. It has chemicals that are used in the hydraulic fracturing process as well as the oil separation process. And it has, sometimes naturally occurring radioactive materials as well as heavy metals and a lot of different organic carbons. So when we think about the treatment of this water and we think about the treatment technologies that exist today, this water is a fluid that really requires us to look at the entire gamut of technologies and figure out how to combine them together to accommodate a fluid that, for one, is very challenging as is, and two, is different across the basin. So there's different qualities of produced water in the Midland Basin all the way to the Delaware Basin in terms of how much salt, how much oil, how much H2S and different bacterias. Therefore, the treatment can be a little bit different for different waters, and the treatment really has to be robust to a water quality that's going to change over time. So those are some of the challenges that we see that we've spent at this point now 4 to 5 years chasing down these different changes that we're going to see in the water. And thankfully, as Texas Pacific has treated this water for internal reuse within the industry, it's allowed us to learn a tremendous amount about how quickly that water changes, what it means when it changes, how we can adjust our treatment systems. But I will say that it is, it's not easy. Produced water, you really do have to be ready for not anything, but for a lot of different conditions, especially in the Permian too. So,
Scott, we're kind of painting the macro of this picture. Tell me if this is a flawed way to think about it. We have been taking this water and largely re-injecting it. There's only so much space to do that, and we're getting, the volume of it is going up as particularly Delaware production goes up. And I think we're producing from more and more places that have even higher ratios of water to oil. So the whole thing it's sort of like a parking lot that has less and less spaces every day. And we're going to have to expand the lot or get smaller cars, or we got to do something. Is that the way to think about the water problem? Is that how you think about it?
I think that's good, Maynard. I mean, you draw nice analogies, and a parking lot is one. We're filling up with cars, but nobody ever leaves. They're not going away at night and coming back the next morning. You just keep putting more water in it. So it's a big subsurface volume, and we are having to move it farther and farther now and find new horizons. So the cost of disposal, the economics always comes in. The cost of disposal is going up, that cost per barrel. Today, it's much cheaper to dispose the water than it is to desal and build a pipeline and do something. It's just cheaper, the economics. But the disposal cost is going up, And the desal and movement cost is going to come down with economies of scale. And particularly, Adrian did a beautiful job of describing everything in there. Some of that stuff's valuable. There's value to that water. And so it creates new industries and new opportunities, and it allows other industries. So AI, some people in Texas want it, a lot don't. It turns out the governor's put a little moratorium on discussions for a while. We'll see how that all goes, but nonetheless, but even power. We're building more natural gas power plants now, and those need water for cooling. Okay. So the beneficial use of this for several decades is very high. The economics start to work, and it's those multi-industrial uses that Texas would like to see. That's all tax base. That's all jobs. And that's exactly why the federal government, through the Department of Energy, wants to see Texas solve this problem, because that's oil and gas for the nation. And we need to keep that going. That's a given. That industry needs to continue to do this. So the question is, who leads? Who's going to drive this forward? And we can talk about which dominoes fall first, Maynard. And I have opinions about that, and others do too, but we can talk about that. And what Derek does, he can tell you when we get to that a little bit, he works a lot with his company, Agnostic Data Group, across sectors, but a lot with the ag industry. And the demand for water there is tremendous. So there's opportunity here.
Maybe we'll just grab that real quick, because Scott, you referenced non-food crops. And so I started thinking about barley. I don't know if that counts, but I went right to beer. But talk to us about, so we get this water, how much you have to clean it up to start using it. There's stages, right, of cleaning it up. You can use it for various things as you clean it up. But maybe Derek, if you don't mind talking a little bit about the agricultural angle here, just to get that on the table.
Sure. From the ag side, and we're focused on the Ogallala because as far as an aquifer goes, the recharge rate on the Ogallala, as Scott mentioned, is low. So when you pull the numbers for ag use in the Great Plains region, it comes out to about 36 billion barrels a year. So that's the total across the plains. But when you focus on non-food crops, cotton alone demands about 8 billion barrels a year in the Ogallala region. And then we can even talk more about economically viable water in terms of how far away from Permian that the water will be. But the 9 surrounding counties closest to the Permian use close to 3.6 billion barrels of water a year in cotton alone. And I have the cotton numbers, but we've got other non-food crops, but the major non-food crop is cotton in the region.
So 3.6 billion barrels a year, if we do the math on that, that's more than cleaning up all the produced water in the Texas Permian. Let's pretend like you can clean up half of it, That'd be a couple billion barrels, I mean, or 2 to 2.3 billion barrels a year of cleaned up water that's useful. And cotton alone in 9 counties needs over 3 billion. So that's pretty slick.
So do you mind telling, while we're on this topic, and Adrian, jump in here, but to use this water in cotton farming, how much do you have to clean it up? How do we think about that technology? Adrian?
I can take that. So we've actually spent the past couple of years growing alfalfa. So we grew alfalfa in a greenhouse, as well as some native grasses and native plants, to really understand that question, which is how much do we need to clean up this water in order for it to be useful? So what we did is and something that you mentioned I want to go back to is that along the way of treatment, at these different qualities, you can do different things. And that is true, but when we start thinking about application in land or application in water, what we've found in our research is that we really do have to go all the way clean and then add these minerals back as we need them, as opposed to somewhat going halfway because of the variability of produced water. So what we found in treating water for use in agriculture with things like alfalfa is, as we know, desalination of produced water is going to create a brine solution. And that brine solution has valuable minerals in it, even from an ag standpoint. We have a lot of things that we can use as fertilizers. And so what we found in our trials in utilizing that brine to remineralize the water and essentially add, a existing fertilizer back to the stream is that fertilizer stream of brine was unpredictable and can have metals in it. And so what we've determined is that we have to go through the full rounds of treatment, going from, say, starting about 150,000 TDS, total dissolved solids, through normal pre-treatment removal of things like oil, solids, bacteria. And then from that point, we go into a desalination system. So our desalination system, our first step is freeze desalination. That's a technology that we've developed here at Texas Pacific. We developed that technology to get down to a salinity that is workable with existing technology. So we go from that very high salinity, 3 to 4 times the ocean, about 150,000, down to about 30,000, 20 to 30,000 TDS. That's about the ocean. Then we'll switch to traditional seawater reverse osmosis, which gets our water now down to very close to drinking water quality. So at this point now, we're around 300 parts per million. The majority of that is going to be salt, calcium, magnesium, maybe a few other minerals. So at that point, the water is very clean. After polishing and such to remove any traces of things like ammonia and VOCs, that water is usable in almost any scenario that we've did it in. We've done testing with human cell lines, with different plants, with different soils at different depths and application rates. And so at that level of cleanliness, the water presents a tremendous opportunity. So much so that even to go back into to the Pecos River, like Scott mentioned, or onto crops for either crops or rehabilitation, we actually have to get some minerals to add back to that water. Now, the exciting thing is that is a tremendous amount of those minerals existing in the brine stream. So it's just a matter of recovering those and, bringing it all together.
So one question for everybody, because you alluded to this, Scott, you can't do the quick math. You can't say 20 million a day times 7, times 52. You got part of it you just can't save. So you're going to be left with the really bad stuff to get the good stuff. What do you do with the really, quote, bad stuff? Once you've gotten all that stuff out of the water and you've gotten this great water, what happens to the bad stuff?
Well, the brines, 150,000 is a lot. Like Adrian said, 4 to 5 times seawater. So let's say you desal half and the other half remains. Now it may be 300,000. That's briny stuff, but you can still inject it and dispose it. It's a volume of water. It's not a block of salt that a deer is going to come up and use as a salt lick or anything. It's just pretty briny water. So you can still dispose that. It just cut your volume of disposal in half, which is a really big deal. Had we started doing this a little earlier, we could probably have mitigated this completely in many ways, depending. But we don't do that because you have to have the economic drivers and you have to have the lessons before everybody's willing to move on it, Maynard. But unlike, some people have to actually dump those salts at the surface. I mean, I think the leader of desal in the world has to be the Middle East, around the Persian or the Arabian Gulf, depending which side they live. They desal all their water to drink. Any water they have, they've desaled. So they have to, you'll be able to walk across the Arabian Gulf soon because it's going to be so dense. You can hardly float in it without paddling. But so we're not talking about crazy numbers here. We're talking about cutting volumes of water in half for disposal and then use, as Adrian says, for lots of other things. And it's kind of ironic to think about having to pull it all out and then putting some back in. Yes, that has to happen, but hopefully the value that comes out of that for various things gets moved into different sectors, and people realize the rents along the way, which motivates us all to play in this game. it really becomes a matter of who's going to drive this, who's going to trigger this to happen. And I have an opinion about who needs to do that. So yeah.
Well, it's hanging there. So let's
Yeah,
grab it. I guess listening to you, we could have it could be driven by oil and gas has to pay more to find ways to deal with the water. Agriculture needs the water, so maybe they need to pay more to get the water. But let's talk about what or the government subsidizes or otherwise comes over the top and forces some of these things. And then there's always technology angles that could change everything. But how do you see the dominoes falling here? That's for everybody.
Well, I think, one of the biggest challenges in my opinion was something that we are getting over now, which is the research side and fully understanding everything that's in produced water, what it takes to treat it, and getting the public and regulators comfortable with that. And then the other side is the techno-economic analysis, development of a technology that can scale and that will fit into the market that's required to bring produced water desalination to fruition. So, in the Permian, it's very challenging from a power standpoint. It's very challenging from a spatial standpoint, and depending on your discharge method or your options of what to do with that water, we really only have one river in the Permian that we could discharge to. And when it comes to land discharge in the Permian, there's a lot of land in the Permian, but there's also a lot of infrastructure here. It may not appear that way when you drive through it, but there is, tremendous amounts of pump jacks, pipelines, and, operations taking place that stop you from having these large, thousands of acres of contiguous land to apply this water to. So I think there are, challenges in the Permian with location, access to power, co-location, and finding benefits for the water as well as power or waste heat. And I think those are things that are, kind of, and the regulatory space as well. We definitely need to finalize the regulation in terms of what produced water treatment needs to meet in order for all of us to finalize our systems and pitch these and grow them larger. So I would say that those are some of the low hanging fruit, in my opinion.
Before Scott does dominoes, Adrian, would you just talk about the regulations around once you clean up the water, you can't just start using it. Like you've got to get approval. Do you mind just talking about that piece of this?
Yes, absolutely. So we've been working on the regulatory space now for about 2.5 years. The two options that we have right now in Texas are land application and surface water application or surface water discharge. So those two permits, the surface water discharge permit is a TIPDES permit. TIPDES is Texas Pollutant Discharge Elimination System that is managed by TCEQ, the Commission on Environmental Quality. So they regulate everything that it gets discharged into surface water to be protective of aquatic species, of downstream users. And so that's a very highly regulated permit. There's a lot of standards that already exist for Texas surface water quality, as well as standards that are currently being developed with companies like myself, consortiums in Texas and New Mexico, a lot of university involvement and papers to try and inform regulators as well as industry operators on what those finalized produced water treatment standards have to be to go into surface water. The other permit that we have, or the other option that we have, is land discharge. So as of right now, that permit used to be with Railroad Commission. It changed in the last session to be under TCEQ's jurisdiction. So now that permit is called the TLAP permit. It's a Texas Land Application Permit. That permit is also now managed by TCEQ and is also still in development since it got shifted from Railroad Commission to TCEQ. But the good news there is that we've had a very long industry speaking, we've had very long working relationship with TCEQ at this point in working through the surface water discharge piece and permitting. So a lot of information has been shared now with them, to inform the way that we look at these permits long term from a reporting standpoint in terms of data that we're going to share with the agency, extra testing that we're going to do that's not standard in every industrial discharge permit, but things that we're doing on the produced water side, just to be extra careful since this is going to be one of the first operations of its kind in Texas. And so we're making a lot of progress there. As of right now, there are 5 permits in queue to discharge into this local watershed in the Permian. So that's around Red Bluff Reservoir. I believe at the moment it is over 1 million gallons a day that's in permit queue to be discharged to that local region.
So Scott, we had this looming dominoes question, and then Mike and Robbie need to jump in next. But we were talking about, what triggers this to
Sure.
who goes first?
Sure. Let me just try to describe it simply. There's the production of fluids. So the oil and gas operators own the oil and they own the gas and they own the water. If they weren't there, this doesn't happen. So that water now gets separated, and there's a midstream water industry. They take the water ownership and they move it and dispose it, or they might move it and clean it up and then dispose it and use it. And then it starts going off into different end users, Maynard, which we've talked about most of them already. So right now, the industry itself, which is the owner and the powerful component of this, needs to drive this. They need to say, yeah, it's going to be more expensive for a while than disposing it. But to maintain our license to operate, we've got to do this. Because even in West Texas, they don't like earthquakes. And they certainly don't like salt water bubbling up to the surface on their ranches. Nobody does. And industry knows this. So it's really a matter of the rate of acceleration towards this. We have the technologies. Nothing we've talked about today is weird technology. This is all doable. It all exists. We're scaling desal. I mean, 1 million gallons a day is a lot. We're talking about 20 million barrels a day. So the scaling has to happen. The regulators have to get ready. Texas needs to probably incentivize, particularly certain groups like ag. Ag literally loses money every year. They can't afford more than about a dime. So they're not going to be the big payers for all of this. They might be able to afford a little bit more. AI will pay for water. Power centers will pay for water, generating electricity. But at the end of the day, I think industry needs to visualize this decreasing cost of desal and increasing cost of disposal. And that's why the National Petroleum Council, in which I've sat for over 2 decades, has a huge produced water study going on right now, and I'm on it. They're looking very hard this year at this challenge and this opportunity. The ownership of everything in that water is actually been under huge discussion and debate, but I think it's gone toward the subsurface. I think it's just like the oil now. The mineral owner owns that, and industry, etc. So the values that come out of that brine stream are going to be there once we start managing this. We've got to get it going, though. If industry gets behind on this, then I think the regulators drop in and say, hey, we're going to tell you what to do, and you may not like it. So I just feel very strongly that industry is in the driver's seat right now if they'll just get in there and drive, Maynard. Let's go, okay? We know what to do. We really got to start going to scale, not little pilots or experiments or prototypes. Like, let's go to scale now and do this. And Adrianne, I'd love to hear your thoughts on it.
Yes, absolutely. I'm with you there, because scale, the quicker we can get to scale, the quicker we get to, a more favorable economic situation. However, the regulatory piece, I think, is a big hurdle in getting to scale, because as I mentioned, currently right now, we've just almost finished construction on our 10,000 barrel a day desalination facility here in Orla, in the heart of the Permian. And we, technically, if we were to be operating that facility and producing 5,000 barrels of this treated water a day, I still have very little options of what I can do with that water. So that's a challenge in bringing these projects to scale, because you really are, taking some risk in, especially on our side, taking some risk in going forward and, putting out the capital to build a site of this size, and hoping that the regulatory framework is going to follow the same pace and that the industry is going to follow the same pace. But like you mentioned, Scott, we have to start somewhere. And so at Texas Pacific, we started with a small pilot so that we could start getting this information out. That was the biggest priority of ours, was just, let's just share that the technology does exist. Let's answer that question, that it is possible to get water to a very, very clean quality. We've been producing deionized water for decades now, so that we know that the technology is there. It's more a matter of, and the reason why we went forward with building a 10,000 barrel a day facility is that we wanted something that was, not a small little pilot, but not large enough that, we were hindered by things like regulation and time and pace of the industry. At 10,000 barrels a day, we felt like this was a good enough size that we could start demonstrating some of this technology at scale. It's a smaller scale, but it's at a scale that, is semi-commercial. And it allows us to actually start studying these, what we think is necessary for, desalination, which is co-location benefits. We know that these projects are coming to the Permian. We know that desalination is extremely expensive. And we think that this co-location analysis and, getting that data out will be really important in driving the speed that people start investing in desalination and considering desalinated produced water as a long-term source. So yes, very, very excited to get this 10,000 barrel a day site up and running. I think, I can speak for the industry partners that we have and the groups that we work with, as well, that they are too, because I think all of us are really just waiting to see something on operating, producing clean water at scale. And so that's what we're really hoping to bring. And, until we do have the permitting ability to put that water in the river, we will likely just stick to rehabilitation, continuing our rehabilitation projects and research for now, but, still very much gathering data and sharing that data with as many people as we can.
And Maynard, just one quick thing here. Full disclosure, as always, I'm an advisor to a company called Crystal Clearwater Resources. Same kind of scale, 10,000 barrels a day. There's enough water for lots of companies in this space. I think the big thing that Derek has learned from the cotton side, only took the cotton folks 100 years to learn this, is you have to take the water from where it's produced all the way through to the end use and measure its volume and its quality at some level. And it has to be an independent group. He does this for cotton. That's what his systems do, so that there's fidelity to it. There's trust in the regulatory that this is being produced. This is the quality. We might be putting stuff back in. Here's where it's going. Here are the volumes. And now everybody believes this from an independent group. And maybe even the DOE wants an independent chemical lab even to say, yeah, on a random sample basis, that's actually what they say they're doing is what they're doing. And so there's a couple pieces in here that I think will sound a little onerous at first, but actually are going to grease the skids and facilitate this happening at scale much quicker. And that's the kind of thing Derek's been doing on the cotton side, and it's very doable on the water side.
Yeah, maybe, I don't know. This may be a question for Scott or Adrian. I think we maybe should have asked this or stated this at the beginning, but, Scott, you've been talking about the disposal costs are here and they're going to be rising quite dramatically if we don't do anything. You're talking about desalination prices coming down with technology over time. Maybe just kind of level set, what is the average cost of per barrel of disposal today? Where is that going in 5 years, and vice versa? The desalination, where is that? Where can it go? I mean, where does that intersect? Thoughts on that?
Yeah, it depends on who you ask. them. but you know, Mike, you look at about probably 50 cents, 25, 50 cents to a buck a barrel for disposal. And you're looking at $3, maybe 2, maybe 4 for desal. So you're looking at 2, 3, 4x. That's a lot. I'm not making light of that. But the buck a barrel side is going up because further distances, lower rates and volumes, the aquifers aren't as good, etc. And then again, that license to operate, as the ad says, priceless. So what's the value of a license to actually operate? On the desal side, as these 10,000 barrel a day modules come on in different technologies, we're for sure going to see that coming down. I mean, that's just what's going to happen with scale. And then once you put the infrastructure in, like building a water pipeline to non-food crops, the compression or the motors and pumps that are needed to move that water, it's heavier than oil, and et cetera. Once they're in place, that really starts to set some of the early costs, the capital costs, and then your per barrel costs get kind of coming down across there as well. And then who pays? I think AI is willing to pay a lot right now. Maybe power gen a little less. Ag could pay more than they're currently paying. And there's so much water, Mike, they might even be able to do 2 crops a year. Right now, cotton is only 1 crop a year. They're water limited. But they could use all the water. Now, it'll take us some surface ponds, line ponds. Let's put those out there on university lands. I mean, I can draw this picture pretty simple. But all of a sudden, you get 2 food crops or 2 cotton crops a year, and they're paying more. So there's the economies start to kick in when, as Adrian says, you give me somebody who will take this water and we can clean it up. And TCQ will probably say, well, we'll permit it if they'll take it. It's just this dominoes that are waiting to fall. And that's why I think industry needs to say, let's go, TCQ, let's go. Railroad Commission will have a little bit of say in it. Let's go. We're ready. And then I think you're going to start to see that happen.
Yeah, and the other thing is we were at the Ham Institute 2 weeks ago, and one of our one of our employees, I guess, Nick Morris, he was there, he was moderating basically a produced water panel, and it was interesting. There was a lot of discussion, a lot of agreement, but a lot of disagreement as well. But there was one company that was there that basically said that they were getting lithium, out of here, and they were basically, company, and they were selling this commercially. And it really goes back to the point you just made earlier that it's not all about expenses. There's some revenues in there as well. If we start to think about this, maybe talk about that as well.
Yeah, and Adrian, you're the expert here, but I mean, Smackover Waters have great lithium in East Texas. It's a concentration thing, but if you're moving that water through anyway, and then you create the technologies to extract stuff like lithium, go to scale with it. Now I'm in the battery world. Okay, but Adrian knows all the different value chains here.
Yes, there are a tremendous amount, and to be honest with you, when we started looking into desalination from an economic standpoint, we saw those things like lithium, iodine, ammonia as things that we knew were always that they've been in the water and they're going to exist in the water. And so now that we've gotten to a point where we've perfected our desalination system, we are investigating the brine for these different minerals and things like lithium, things like iodine. And the exciting thing about lithium, I will say, is that a lot of the pretreatment that is required for lithium extraction is almost exactly the same pretreatment that's required for oil and gas to reuse the water. And the lithium extraction is a relatively passive process. And so we have a lot of recycling of the 20 million barrels that are generated in the Permian every day. We're recycling 5 to 6 million of that already and giving it back to industry. And that water that's recycled and treated can be passively put right through lithium extraction and sent back to industry. Or sent to desalination. And so it's an exciting co-location opportunity, along with things that reduce our power consumption, co-location with data centers, recovery of waste heat. Waste heat is really exciting too, because we know that there's going to be these large scale power generation projects heat is really important in the brine concentration piece as well. And clean water is very important in the lithium refining piece and the minerals refining piece. And so, we really are excited about bringing all these things together, because even when we think about something like the extraction of lithium, we have an opportunity to extract and refine lithium that is not dependent on fresh water at all, because we're able to provide that clean water from our desalinated product and the lithium brine stream that is now compounded from our brine. So, yeah, very exciting to see where these are going to go. But it's another thing, another opportunity that we have with produced water.
I guess, I think we've done a good job covering the technology around cleaning and whatnot. But the one thing I wanted to hit on is more on the data and monitoring side of things. Scott, I think you'd mentioned with the seismic activity, you being part of the TexNet, to monitor for seismic, which really allowed, regulators and the community to get comfortable with injection. I wonder if there's similar conversations around beneficial reuse, and what type of monitoring systems or programs are we going to need to deploy in Texas to make the community, feel at ease that Adrianne, you and others have the technology, you're cleaning it the right way, you're not impacting the communities and whatnot. I don't know if, Scott or Adrianne, if you guys have heard much around that, and is there an activity or a program around monitoring of beneficial reuse?
It's being built within this new TIPTES framework that is specific to produced water. So there are monitoring requirements that are slightly different from what is, normally in an industrial discharge system. So some of those things include in-stream monitoring, more in-depth in-stream monitoring for any surface water discharges. We've also worked directly with university now for our land application plot, and have also met with TCEQ about this to tell them that we have installed additional monitors for soil moisture, for total organic carbon, for different gases in the water and in the soil. We've also installed a lot of different and are also implementing AI to start, predicting things like instrument failure, predicting things like membrane corrosion or membrane scaling. And we do that with a lot of different kinds of monitoring. But, some of the things that we are starting to implement as well are on the power side. So we've installed now power monitoring equipment that can actually tell us what is driving our power usage, as well as when we should expect equipment failures or changes in our water quality. So one of the biggest things that, is important for us to determine, one from a water quality standpoint and two from an energy use standpoint, is what is driving that? Is it a certain contaminant? Is it a certain temperature? Is it a condition of the water? And how do we chase down those things to make sure that they don't present problems later on? So AI is going to be tremendously helpful in that sense that, I can't go and look at data that's been taken every 30 seconds and do that every single day and make assumptions. But the good thing about, implementing AI into our SCADA system and reviewing the massive amount of data we're capturing is that it does offer us a tremendous amount of protection too, from a water quality standpoint.
And
making sure. Oh, go ahead, Robbie.
Are these continuous monitoring systems? And then is the information going to be publicly available so everybody can see the results of the water quality?
So the information is publicly available that is reported back to TCEQ. However, these are constantly pulling data. So they're constantly going to be getting data points, some of them every 30 seconds, some of them every minute. And so that tremendous amount of data is not necessarily shared, but what we do is we take that, and then that's when we work with our university partners to make inferences about that data. And then, when it gets to publication, or if it's something that we're sharing with the regulatory agency, then that's when that information would be shared. But we have shared, we've had 4 publications that have been released the past 3 years that include data from our pilots. And so we did, it's called the NIPDES Plus analysis. NIPDES is the National Pollutant Discharge Elimination System. The consortiums made a list of essentially every contaminant that we could test in the water. And myself and other treatment providers have analyzed that list multiple times. And that has been shared with the public, as well as with regulatory agencies. And we've also shared it with universities so that they can compile it into a public report that can be shared with everybody, so that we can offer some reassurance that we have a very good understanding of what's in the water and what has to be removed.
Cool. So Turek, we're talking water and data. That is your world. Anything you'd add to all that?
Sure. There needs to be a way that we can share this with the public actively, because I think that can help build the trust. Right now, there's a low level of trust in the area for what the water coming out of these systems contains. We can figure out a way to stream some of this data to prove that the water is being cleaned in real time. And it doesn't have to be complete quality reports. It can be, we agree on a few good data points that we actively monitor and publish. I think that would help increase the trust in the cleanup operation over time. From my standpoint, we do this already in the cotton industry. There are several different stakeholders around each bale of cotton. And so what we agreed on is that each titled bale of cotton, we would sample, the USDA would sample, and we publish that data coming out of the USDA, so that every bale of cotton now leads back to a quality unit. And so I think if we can get to a point where we're doing a similar thing with water, that will allow the water to flow digitally as well as physically. So we know what's inputting into the system. And in many ways, this is kind of like a grain elevator, where there's a definable amount of water that's entering the system. If we know what's entering the system, we can then defend what's coming out of the system. But yeah, I think that needs to be.
Well, Derek, if you guys also, in addition to the water quality, track the benefits, that could also have a positive impact.
There you go.
The community getting behind. It's like, hey, we've created this much water instead of taking from the aquifer.
I love the expression.
I think the opportunity here from a public standpoint for the oil and gas industry is tremendous, because you will be the first credible, if we can get our heads around this and actually do, this is the first credible input of water in history in the region. I mean, that's a big deal. And the public will notice that.
The industry
and
would be the good guys.
Even the data centers may need that too.
Absolutely.
Right? So like this is a win for oil and gas, but also data centers and the public.
People downstream on the Pecos, they want to know what water is going in.
Mm-hmm.
If you're growing cotton, you want to know what the water is like. If you're growing alfalfa, if you got a data center, if you got a power plant, you need to know the quality of that water for your operation. And it's what Derek does is captures all of that and makes it publicly available. I think you got your quote of the podcast, though, mate.
No, I did.
There's a digital stream and there's a physical stream.
Allowing the water to flow digitally. That was a good one. It's hard to let you guys go. It's such good stuff. Adrianne, is there a quick answer to a unit, the amount of power needed to desalinate a gallon of water? Like, is there just a ratio for just how people understand? It's very power intensive. And so some stat like that would be great.
Okay, I can say in our initial pilot, we were using an average of say 4 to 9 kilowatts per barrel of water. And we get asked a lot too, how much does it cost to desalinate a barrel of water? Yeah. And I always ask, well, how much did that kilowatt hour cost? Because, we have fluctuation in the kilowatt hours just based on the amount of salt in the water, because it's either going to have to get hotter or colder depending on your technology. But I would say that during piloting, we're somewhere around 4 to 7, but hopefully at scale, again, those numbers improve. So when you're working so small, your systems are so sensitive to changes, but as they get larger, you don't have these big swings in energy usage because you have a lot larger system.
And the power you're using at your site, which we're excited to come see in August, what is your power source there?
So we actually have a hybrid system. We have 1.4 megs coming in of line power, and then we have an additional 5 megs being generated with natural gas. And we do that. We have this hybrid system because one, line power is hard to come by in the Permian. And so we wouldn't have been able to power the entire facility with line power in the time that we wanted to get up and running. And then the waste heat side does also offer us a lot of opportunity from a research standpoint to start utilizing it within our facility to either further compound brine, to add capacity to our freeze desalination system, help with RO efficiencies. We see a tremendous amount of benefit in using gas generated power.
And Maynard, crystal clear water. I mean, they can run on waste heat. There's a lot of waste heat in the Permian, a lot. And Adrianne's exactly right there. So some combination of things. But man, if you can use some waste heat and for the desal, and then back it up with other things, that's a win, because you're not having to just waste it, if you will. Scale is the big driver here. We're going to see these things happening, and that's going to continue to bring price down and opportunity up. We got to knock that first domino over, and I think industry needs to go ahead and push that domino and say, all right, let's go. Let's go. It's time. And I think the other big thing you've seen protests. I mean, there's a lot of, I have pictures of AI protests in Texas, and it's not the people protesting fracking and climate change. It's rural people. They don't want the Ogallala being used on these big data centers, and perhaps they are a little worried about AI itself. There's a lot of, I'm not trying to oversimplify, there's a lot of complicated reasons that people are scared. But if you can create the fidelity, the digital fidelity of this water, and show how it is not only going to not take the aquifer, it's going to rest the aquifer, you will mitigate a lot of that. So the Googles and the other big tech companies who are out there doing town halls could wave a very different kind of flag, one that seems more sincere and more genuine than is currently being perceived by the public. And I say perceived, okay? They're being sincere and genuine, but it's the perception that matters. My perception is my reality, always has been. So they need to show that they are, the whole industry needs to show it is tracking this water quality and quantity from tip to tail so that people can trust it.
Has anyone looked at using renewables in desalination? Because it seems like the kind of thing where if it's intermittent, fine, the process will be off for a while. Like, is there any angle there, guys?
Sure, especially in windy West Texas, and you can have it all. You're always producing water, so you could turn it on and off. But I think the combination of wind and then with line or on site behind the meter gas, waste heat, this combination of things can allow it to run all the time. And why not use excess wind if you have it, or some solar if you have it? It's fine. I think that it would be a good thing to do, especially on the wind side, as we sometimes have just too much wind, right? So let's run on that. But you have to have some. You can kind of turn it on and off, but you're always producing water.
Right.
So once you get a system going, yeah. Go ahead.
As the systems get bigger too, it's a lot more difficult to just turn things on and off as well. That's something to think about, especially from a power use standpoint. When you start having systems that are changing frequently like that, that's when you start getting this very high power demand. But oh, go ahead.
If we get to scale with a facility, how big is that going to be?
I mean, for scale for us is somewhere around 100,000 barrels a day. We would like to intake, and I think from an economic standpoint too, that's when things start working out a lot better, is when we get to that 100,000 barrel a day mark, and we're able to start utilizing, these different inputs at scale, as well as, producing a large amount of water at scale too, because at a smaller scale, say 10,000 barrels a day where we're at right now, we'll only be producing 5,000 barrels a day, which, does present some opportunity, but not like it would if we were producing 50,000 barrels a day of a very pristine, clean fluid. So I would say scale for us is 100,000 barrels a day. However, that's not a limit. I would say that we need a tremendous amount more of desalination. Some of these sites are even being proposed in the 400,000 barrel a day realm. So, sky's the limit when it comes to produced water desalination volumes, in my opinion.
And even at the 400,000 barrel a day or 500,000 barrel a day, you're still looking at 40 of those to do 20 million. So this is a big industry, a big industry.
Well, we could go on and on. There's a lot here, but we wanted to do exactly what we did, which is just to get the big picture out there, point to some of the challenges, but also the opportunities. I know, Scott, you'll continue to be all over this issue. Derek, your work too. And then we're going to visit Adrianne in August and see her pilot facility. So we're just super excited about all that. So thanks to everybody for a great show. That's tremendous.
A lot of fun. Very good.
Ideally, I should drink a glass of water at this moment that was,
I'll
cleaned
serve
up.
you guest.
But you already revealed you'd rather have beer. But Senator Hickenlooper, who used to be a governor and a mayor, he drank frack fluid at one point.
I remember that.
Or maybe that was Chris Wright who did that.
I think it was right.
Our Secretary of Energy.
That's so good. Well, thank you all, and thanks to everybody. Stay tuned on this issue. Much more to come on produced water.